going to do some more AP review. This is 2012 BC free response 2. It is BC only because it is parametric, and it is calculator permitted and in some cases required because it is free response 2. So we're given a parametrically defined function, right, where we're given that position is x of t comma y of t for t greater than or equal to 0. At time t equals 2, the position of the particle is 1 comma 5, meaning that x of 2 is 1 and y of 2 is 5, for the record. It is known that dx dt equals the square root of the quantity t plus 2, end quantity, all divided by e to the t, and that dy dt equals sine squared of t. All right, so part A asks us, is the horizontal movement of the particle to the left or to the right at t equals 2? Explain your answer. And then, in the same prompt, they ask us to find the slope of the path of the particle at t equals 2. So let's do this one thing at a time. The first thing they ask about is the horizontal movement of the particle. So dx dt, which we were given to be the square root of t plus 2 over e to the t, represents the horizontal velocity, right? It's the change in x with respect to the change in time. So if we find dx dt at t equals 2, the sign of this answer will tell us whether this particle is moving left or right. Now, it is a calculator permitted section, so you could definitely type this in your calculator and find a decimal answer. I would argue here it's easier to just plug in and get root 4 over e squared. You get a 2 over an e squared, which is definitely positive, right? It's not a 2 over 9, but it's kind of like a 2 over 9 if your brain is trying to quantify this value. All right, so we get a positive value. So since that value is positive, this thing is moving right. When we talk about horizontal motion, a positive velocity means moving right, a negative velocity means moving left. If we talk about vertical motion, a positive velocity means moving up, and a negative velocity means moving down. So we answered the question, we said right, we gave a justification, which is that dx dt evaluated at 2 is positive, right? So first two parts of the prompt, done. Third part, find the slope of the path of the particle at time t equals 2. So slope is always and forever going to mean change in y over change in x, or rise over run, right? Or dy over dx. But when we talk about parametrics, we write that as dy dt over dx dt. Or sometimes you'll see it as y prime of t over x prime of t. My bad. All right, so when we go to do the second part of this question, I want to find dy dx at the moment when t equals 2. So that's going to be dy dt evaluated at t is 2 over dx dt evaluated at t equals 2. Now, we do have a calculator here, and but again, since all you really care about, I mean, it's not wrong to give the answer as a numerical quantity. You can either plug these in your calculator, or you could just plug in sine squared of 2 and put that over the number we just got, because we already did dx dt evaluated at 2. And then you can type this number into your calculator. So you could either use your calculator to physically find each of these quantities and then do a fraction, or you could just find these quantities and then divide in your calculator, and you get 3.055 or 54, depending on if you round or truncate. So that's the slope. All right, that's our part A. All right, let's talk about part B. So part B says find the x-coordinate of the particle's position at t equals 4. So this is actually a first fundamental theorem of calculus problem. So here's what we know. We know from the very first line of information, or I'm sorry, from the second line of information, that the particle's position at time t equals 2 is 1 comma 5. What that gives us is that x of 2 is a 1, right? We also know dx dt, which if you feel more comfortable, you could call x prime of t, it's the same thing, is this thing, right? So, and then we're asked to find x of 4. Whenever you're given a derivative, right, if you're given a derivative either as a graph or as an equation, and you're given one of the two values, like x of something and not x of something else, or y of something and not y of something else, or f of something and not f of something else, this is that first fundamental theorem of calculus, right? So the first fundamental theorem of calculus, usually you see it with f's, right? Usually you see it as if you integrate f prime of x with respect to x from a to b, when you integrate the derivative, they cancel and you get f of b minus f of a. That's the way you're used to seeing this. But it would be the same rule if we integrated x prime of t with respect to t. So in this case, so here, instead of using f of x, what we're looking at doing is integrating x prime of t dt, and the two t values that we want to use are 2 and 4, because we know x of 2 and we don't know but want x of 4. So if I integrate from 2 to 4 of x prime of t dt, I'm going to get x of 4 minus x of 2. And you might say, hey, why is that useful? Well, here's the thing. I want x of 4. I know x of 2. And I can use my calculator to find this integral, because when you have bounds, your calculator can integrate. Now, I'm not a huge fan of using parametric mode in my calculator if I don't have to. So I'm going to be perfectly honest. I'm going to type this guy in as f prime of x instead of x prime of t, essentially. I'm going to type this in where I use x's instead of t's. It's fine if you want to use parametric mode. I'm personally not going to. Your calculator doesn't care which variables you're using as long as it's integrated in the correct equation. So the way I would do this, and you don't have to certainly, what I would say before you even bother is you might as well add the x 2 over, right? So I'm going to get that this is x of 2 plus the integral from 2 to 4 of my dx dt, which is this root t plus 2 over e to the t dt. And that's going to give me my x of 4. Even if nothing else, if you can just communicate this information, that's going to get you a lot of credit on the AP. Again, I don't care how you type it into your calculator. When you're all done with this, right, once you type it in your calculator, you're going to get that your final answer is a 1 plus a 0.253 or a 0.252 in a sec, depending on if you round or truncate. So you're going to get that x of 4 is approximately 1.253 or 2, depending if you round or truncate. Again, when we talk about how to put that in your calculator, the way I personally would do it is I would go into my y1 and I would put square root of parentheses x plus 2, close the parenthesis, divided by e caret x. That's what I would type in, right? And then I would do function integrate of y1 with respect to x, because even though I'm integrating with respect to t in the real world, it doesn't matter what I use in my calculator, from 2 to 4, and that is how I would get this this 0.253 or 0.252. All right, so that's your part B. Let's talk about part C. For part C, find the speed of the particle at time t equals 4. Find the acceleration vector of the particle at time t equals 4. All right, so 2 questions. Make sure you do both, right? So it's important to know how you find speed, right? So the speed that you want is going to be the square root of x prime of 4 quantity squared plus y prime of 4 quantity squared. Not integrated, just typed in. You have some options for how you want to do this. It's honestly entirely up to you. You can type x prime and y prime into your calculator, that's fine. If you were choosing to use parametric mode, again, this is just a preference. It's up to you what you choose to do. If you're in parametric mode, so if you go to mode and you pick pair, then you can use x1t, and you can type your x1t in as the square root of t plus 2 divided by e to the t. And you can type your y1t in as, in parentheses, sine of t whole quantity squared, right? That's absolutely fine. If you type them in there, right, you can type in what values you want to get for these things, right? So if you go to parametric mode, you don't actually need to derive them, because keep in mind that this, when you're looking at this, this was already your x prime of t, right? And this was already your y prime of t. So that's fine if you want to do it this way, right? If you go to mode, and you switch to, make sure you're still in radian mode, but you switch to pair from function, and then you go to your y equals, and you can actually type in what these functions are, and that's fine. And there is an advantage to doing this, and I'm going to show you what the advantage is when we get to part D. So if I type in e to the t, notice that when you're in parametric mode, not only is your y equals different looking, but also your independent variable is t, because it's x comma t comma theta comma n. And then I had a sine of t whole quantity squared, right? Okay, so that's just fine. And one option is that you can go ahead and type it in your calculator if you want. To be perfectly honest, if you feel most comfortable, you could find the value for both of these. It's up to you. Like, you could either type them in, or you could say, hey, I'm not going to bother. I'm just going to get that this is equal to the square root of your x prime of 4 would have been a root 6 on top of an e to the 4th quantity squared. plus this would have been a sine squared of 4, but that'll make it sine to the 4th of 4, right? Because it'll be sine squared of 4 squared, right? And you could just type these numbers in your calculator too. There are different ways to go about this. It depends on whether you think it's worth entering these in your calculator or not. It's up to you. Either way, this is what you're typing in for your speed. And when you do that, right, you're going to get that the speed is a 0.575 or 574, depending if you round or truncate. Okay, so there's your speed. The second thing you're asked to do here, though, and this is why I was pointing out it might actually be very worth it to you to do, to find these in your calculator, right? My acceleration, right, so the acceleration as a vector is x double prime of t, comma, y double prime of t, right? It's going to be what happens if I derive both of those functions again. Now, there's two ways to do that. One is that you could actually go ahead and find the derivative by hand, okay? You could find it by hand, but they didn't ask you for acceleration in general, right? So it's not awful to derive the y prime by hand. The sine squared isn't terrible. It's a simple chain rule. But this one's going to involve a quotient rule, and it's not going to be pretty, and it's going to be kind of annoying. So what I'd suggest is, since they specifically wanted it at the moment when t equals 4, what you actually want is you want x double prime of 4, comma, y double prime of 4, and that's a thing you can make your calculator do, right? So if I quit out of where I was, remember that I'm allowed to take a derivative, right? So I'm going to go to math. If I go to math and I pick 8, that's n derive, right? So I want to derive. So in order to find this, what I'm going to do is I'm going to do n derive. Okay, I'm going to derive what I called x1t with respect to t at 4, right? So I'm going to go ahead and derive, I go to vars, I go to y-vars, and I pick parametric. Well, look, there's my x1t, comma, with respect to t at 4, right? And when I do that, I'm going to get a number. I'm going to get very quickly that this is apparently a negative 0.041. That's the x-coordinate of the acceleration. And then I'm really lazy, so I'm going to hit second enter for the other one. So I'm going to hit second enter, right? Second enter. And then I'm just going to change the x1t to a y1t. I'm going to go to vars, y-vars, go to parametric, and I'm going to pick y1 of t. And oh, look, it's a 0.989. So there's my vector, right? That's my acceleration vector. So again, this is a much harder problem if you're asked to find acceleration as a formula for each of these, but you're not. You're asked to find acceleration at 4, so you can use your calculator to derive. Again, that's one of the advantages to putting these in early, right? Now, I'm pretty sure that you can actually make your calculator put this in too. I'm going to experiment for a sec, but I think that if we go to math, maybe it won't let me. I was pretty sure there was one that had a value, but I don't see it. Yeah, I don't see it off the top of my head, so that's okay. I think this one is probably worth just gutting out and typing it in. The other option you could find, well, let's find a thing. I'm curious if this works. All right, let's see what happens. If we go to graph, okay, if I go to graph this, and if I hit trace, okay, so if I hit trace and then I put in a time when t is 4, so if I put trace and hit t is 4, I get these two values. I get x prime of 4 and y prime of 4, right? So what I'm curious is if these values are now currently stored as x and y. So I'm just going to make a note off to the side that the x was a 0.448 and some stuff, and the y was a 0.572 and some stuff. So if I quit out of this, I'm curious what happens if I press the x button. So you can't use the independent variable button because that's going to be t right now. But if I hit alpha x, I'm curious if it's currently stored as the 0.448. It is. That's dope and totally awesome. And I'm pretty sure that if I hit alpha y, it's currently stored, whoa, as the 0.572. So instead of doing all this stuff, if you put this stuff in, right, you could have hit trace, right? You could have hit trace and you could put t as 4, and you're going to get the two x coordinate, the x and y coordinate correctly, right? You're going to get this x and y coordinate right here. So then once I know those, I could actually type in this exact formula. I could type in the square root of, right, alpha x quantity squared plus alpha y quantity squared, and that should give me the same thing. Hey, boom, right? So that's another great way you can do this. So it is worth putting these in the parametric form for that specifically. All right, let's move on to D. I just got kind of nerded out about the thing that your calculator can do. All right, let's move on to D. All right, so D asks us, find the distance traveled by the particle. Well, that's definitely arc length, right? So D is asking us for the total distance, but remember that total distance in parametric is really just saying, hey, what's the arc length, right? So when we want to find arc length from 2 to 4, that's going to be the integral from 2 to 4 of the square root of x prime of t quantity squared plus y prime of t quantity squared with respect to t. And again, because I've already typed these into my calculator, I'm just going to type this straight in. So here's what I'm going to type. I'm going to press math 9, which is function integrate. I'm going to integrate the square root of x1t squared, because that's what I put in as my x1t, plus y1t quantity squared, close the parentheses, with respect to, with respect to t, because sometimes I get on autopilot, from 2 to 4. Right? So we're going to type that in our calculator. So just to show you what that looks like, right? I'm going to go to math, right? So I'm going to press math 9, right? Square root of. I go to vars. I'm going to go to parametric and pick x1t, square it, plus vars, over to yvars, parametric, pick y1t squared, close the parentheses, comma, with respect to t from 2 to 4, close my parentheses, and I should get a 0.651 and some stuff. We're going to find out in a sec. It's thinking very, very hard. Woohoo! All right, so I get that my answer, right? So again, the AP doesn't care at all for your calculator notation, but you have to know how to do this. I get a 0.651 if I round, or a 0.650 if I truncate. Cool.